Hello there, Cosmic Explorer. In today's video, we are going to explore the mysteries of the universe, understand planets, and uncover the enigmas of dark matter and dark energy. Imagine traveling to the most distant corners of space and time, where the universe's biggest puzzles await. Buckle up, because we're about to embark on an incredible cosmic quest. Get ready to unlock the universe's hidden wonders and expand your knowledge of the cosmos. It's going to be a fantastic voyage. As the 20th century was coming to a close, two groups of astronomers did something cool. They used telescopes on Earth and in space to study exploding stars in faraway galaxies. Their mission was to figure out how fast the universe was expanding due to gravity. But guess what? They found something shocking. Instead of slowing down, the universe was speeding up, and some mysterious force was causing it. This discovery marked a big moment in the world of science. It challenged our understanding of the universe, even though it took a century to reach this point. Einstein's ideas held up. Scientists started to dig deeper into the Big Bang, which is like an explosion that made space itself. We're still not sure how those supermassive black holes in space are born, but we do know they exist in almost every galaxy, and we've built special tools that confirm some of our old theories. It took about 50 years to create a gadget that can detect something called gravitational waves. This helped us understand the universe's future. As we uncover more pieces of the cosmic puzzle, the universe's mysteries get even deeper, and that's what makes science so exciting. Throughout history, humans have been on a quest to understand the universe. With each generation, we've come up with new ideas, tested them, and made them better. It's like standing on the shoulders of giants to get a better view of reality. In the 17th century, a smart guy named Isaac Newton used math to explain the world around us. His ideas changed everything, showing that we're not separate from the universe, but can understand it. Newton's equations explained how everything in the universe attracts everything else. For example, we could predict where planets would be in the future, or even find new planets by watching how they moved. When we saw that Uranus was acting weird, astronomers teamed up to find another planet, which turned out to be Neptune. But there was one planet that didn't follow Newton's rules: Mercury. It had this tricky thing where its path around the sun kept shifting slightly every year. This was called precession. Newton's gravity couldn't explain it, and we had to look for other answers. People once thought that there might be another planet closer to the sun, which was causing Mercury's orbit to act strangely. They even gave this mystery planet the name Vulcan, after the Roman god of the forge. While some scientists were on the hunt for Vulcan, others were searching for a new way to explain why Mercury behaved so oddly. Then, in 1915, a German physicist named Albert Einstein presented a groundbreaking idea about gravity. He called it Einstein's relativity, and it completely changed the way we understand the universe. Instead of thinking of gravity as a simple force that pulls things together, Einstein's theory treated space as something that could bend and warp. Any object, from a tiny grain of sand to the whole Earth, could curve space around it. When other objects moved through this curved space, they followed these curves like they were sliding down a hill. Einstein's theory was like a revolution. It replaced the old way of thinking about gravity and introduced a new way that was quite simple but incredibly powerful. It explained Mercury's weird orbit without the need for a mystery planet like Vulcan. But Einstein's theory needed a big test to prove that it was right, and to replace the ideas of Sir Isaac Newton, which had been around for over 200 years. Einstein's theory predicted that a massive object, like the sun, could bend the path of light that passed near it. The perfect chance to test this came during a solar eclipse on May 29, 1919. The group of astronomers led by Arthur Eddington took this opportunity to check if Einstein's idea about light bending near the sun was true. They went to Brazil and an island off the coast of West Africa to observe the eclipse. During the eclipse, they saw that the positions of some stars in the sky were slightly different from what they expected. This was because the sun's gravity was bending the starlight as it passed near it, just as Einstein's theory had predicted. Einstein was proven right, and this experiment was a big success. Since then, scientists have continued testing Einstein's theory, and it keeps passing with flying colors. For many centuries, we relied on Newton's ideas about gravity, but Einstein's theory has stood the test of time, even in the most extreme situations. So, even today, Einstein's relativity still holds up, and we're amazed that it works so well. It all started with a simple desire to understand our universe better and get a more complete picture of how it works. While we often rely on Newton's laws of motion for our everyday lives, Einstein's radical ideas about gravity become essential when we're trying to understand the universe in extreme conditions, where things get super dense, hot, and dynamic. That's where Einstein's theories shine. Astronomers use telescopes to capture light from objects in space. This light is made up of a rainbow of colors, and we can learn a lot about what things are made of and how they work by analyzing this rainbow of colors. Each object in space has a unique color fingerprint that tells us about its chemical composition and how it behaves. But to understand these color fingerprints and how stars or planets have them, scientists had to rethink what they knew about matter. You see, back in the day, people thought atoms were the smallest, indivisible building blocks of everything. But in the 19th century, scientists discovered that atoms are more complex than that. We now know that atoms have a nucleus at the center, which contains most of the mass, and electrons that whiz around the nucleus. However, according to classical Newtonian physics, these electrons should spiral into the nucleus and destroy every atom in existence. In 1913, a Danish physicist named Niels Bohr came up with a new model for the atom. This model relied on a new concept called quantum physics. Quantum physics is all about the tiniest scales of the universe, explaining how atoms and their parts behave in weird and surprising ways. In this quantum universe, electrons are forced to orbit the nucleus at very specific distances, almost like they're on a ladder with unevenly spaced rungs. The size of these rungs determines the exact colors of light an atom can absorb or emit. Each element has its unique ladder, so to speak. But quantum physics is pretty strange. It tells us that electrons aren't in one specific place around the atom, but they're spread out in a cloud of possible locations. The universe becomes uncertain at this tiny scale. This quantum understanding of the atom helped solve a long-standing mystery of how our sun and other stars can shine. It revealed that even something as familiar as sunlight could be explained using these strange and uncertain quantum principles. So, while we may still use Newton's ideas for most things in our daily lives, Einstein's and quantum physics are the tools we need to explore the universe's most extreme and puzzling aspects, where classical ideas just won't cut it. In the heart of our sun, the conditions aren't hot or dense enough for nuclear fusion to happen, at least according to classical physics. But under the strange and fascinating rules of quantum physics, there's a tiny chance that fusion can occur. The chances are incredibly small, but it's enough to power our sun and all the stars in the universe. When we combine the powerful ideas of Einstein's theory of relativity with the weirdness of quantum physics, we can explain many things about the universe. However, there's a challenge. These two theories, while individually brilliant, don't seem to fit together. When we try to describe really big things, quantum physics doesn't make much sense, and when we tackle small things with general relativity, it doesn't work either. The reason for this is that gravity, as we understand it now, doesn't quite work in the quantum world. So, scientists are searching for a new theory, or maybe some adjustments to the existing ones, to create a unified theory that can help us truly understand the universe from its very beginning. Speaking of the beginning, about 13.8 billion years ago, everything we know was born from a single point in an event known as the Big Bang. This wasn't exactly an explosion into space, it was more like an explosion of space itself. Over time, the universe expanded and evolved, stars lit up, and galaxies formed. Today, our advanced technology allows us to observe many of these cosmic moments, but there's a barrier we can't cross. About 380,000 years after the Big Bang, the universe was so hot and dense that atoms didn't exist as we know them. Instead, they were ionized and formed a plasma that acted like a fog, preventing light from traveling. It wasn't until the universe cooled and expanded that this fog cleared and light started flowing freely. This ancient light is known as the cosmic microwave background. Surprisingly, the discovery of this ancient light came not from seeing it, but from hearing it. Back in 1964, two astronomers thought they had a problem with their radio equipment. They spent a long time trying to figure out what was causing the interference in their data, even thinking it might be bird droppings. Eventually, they realized they had discovered the cosmic microwave background, a relic from the Big Bang. The cosmic microwave background is incredibly consistent all over the sky, which implies it was created in the same place and confirms the Big Bang theory. It's like the universe's fingerprint of its birth. As we look back in time, we reach a cosmic barrier about 380,000 years after the Big Bang. To understand what happened before that, we rely on scientific theories and models, which combine the power of Einstein's relativity and quantum physics. But at the very earliest moments, when everything was crammed into an unimaginably small point, our equations break down. We need a new theory or a significant adjustment to the current ones to explain what happened at that incredibly tiny and concentrated point. The universe holds other mysteries too, where our understanding of physics seems to fall apart. Black holes, for instance, are so dense and have such intense gravity that nothing, not even light, can escape from them. When it comes to these extreme objects, our current theories struggle to provide complete answers. So the quest for a unified theory continues, a theory that will help us understand the universe from its very beginnings to its most extreme and puzzling corners. It's a fascinating journey that may eventually reveal the secrets of the cosmos. In 1971, astronomers spotted a strong source of X-rays known as Cygnus X-1, and after a thorough investigation, they concluded that it was a star orbiting a black hole. Soon after, another phenomenon, Sagittarius A*, located at the center of our Milky Way, was thought to be a black hole based on its intense radio emissions. It's important to note that the black hole itself doesn't emit these radio waves, but rather, it's the matter surrounding the black hole, spiraling in and generating heat and light as it gets closer. While we can't directly see black holes because they don't emit light, we've been able to measure their presence and mass by observing the gravitational effects they have on stars orbiting around them. For example, the supermassive black hole at the center of our galaxy has a mass about 4 million times that of our Sun. Supermassive black holes, found at the centers of most galaxies, can be even more massive, some with billions of times the mass of the Sun. To study black holes, an international collaboration called the Event Horizon Telescope, EHT, was established. It uses multiple observatories around the world, combining their data to create an incredibly detailed picture. While they haven't captured an image of the black hole itself, they've observed its shadow, measuring a diameter of about 100 billion kilometers. This shadow represents the point of no return, where everything is drawn into the black hole. Even though we can't fully explain black holes until we have a unified theory of physics, scientists have developed new methods to study them. One groundbreaking method involves detecting gravitational waves, which are ripples in the fabric of space itself, caused by mass accelerating through space. Gravitational waves were predicted by Einstein in 1916, but were considered almost impossible to detect due to their incredibly small size. In 2002, the Laser Interferometer Gravitational Wave Observatory, LIGO, began its search for these elusive waves. LIGO uses massive L-shaped detectors to measure tiny distortions in space caused by passing gravitational waves. The challenge was isolating these distortions, smaller than an atom, from other sources of vibration. LIGO set up 2 detectors on opposite sides of the United States to confirm signals, and after years of silence, they made their first detection in 2015. It was the result of 2 black holes in a death spiral merging into one. The observation matched predictions made by Einstein's theory, and it marked a significant milestone in astrophysics. The second detection was even more exciting: a binary neutron star collision. Unlike black hole mergers, neutron-star collisions could be observed not only with gravitational wave detectors, but also with optical telescopes. Astronomers worldwide pointed their instruments toward the source, creating an avalanche of data. This approach, called multi-messenger astronomy, combines information from different sources and phenomena to gain a more comprehensive understanding of the universe. The future of astronomy looks bright, with the potential for even more powerful gravitational wave detectors that could help us uncover the universe's earliest moments. There you have it. If you could explore any part of the universe or a particular cosmic mystery, where would you go and why? Let us know in the comment section below. If you enjoyed this video and found it informative, make sure to hit the like button and subscribe to our channel for more engaging content like this. Thank you for watching.